also its sun because we talked about how much you would weigh on a given planet or on the moon. And from knowledge of the composition, we can speculate about the formation history. And then, of course, many planets have moons. Most of the moons are contained around the giant planets in the outer solar system. Most of the moons are actually between Jupiter and Saturn, and there's only a relatively few others around those planets. All right, so again, comparing things to Earth-type units, we see that, again, if we look at Earth here, it has 20 units of mass, that's Earth's mass unit, 20 units of radius, 20 units of density. If we look at Mercury and Venus, we see the masses are a bit, well, Venus' mass is just a little lower than Earth's mass, but Mercury's mass is tiny, only about a 20th of Earth's mass. And the radius of Venus is very close to Earth's radius. Mercury's is smaller. Mars is about half Earth's radius, so Mercury is just a little smaller than Mars, but all the inner planets have a density pretty close to 1 Earth unit. So their composition is probably very rocky with a dense core, just as the Earth has a dense core of iron. We think the other terrestrial planets have a dense core. But we do start seeing a transition happen when we look at Mars, because Mars has a density only about 70% of Earth's density. And then if we go farther out to Jupiter, the density plummets down to only about a quarter of Earth's density. So Mars is starting to indicate a kind of a transition as we move from the inner rocky solar system into the outer solar system and start seeing less and less of a dense core in any of these planets. So Mars' core is a lot less significant in its composition than Earth's core is. So this is an example of a phenomenon that we'll talk about that occurs in many different situations where we have bodies that have become molten for a period of time and are subject to a gravitational field. It's something that we call differentiation. Differentiation generally causes denser materials to stay closer to the source of gravity. So in this case, the source of gravity is the sun. And we see the denser planets are near the sun because the denser material tends to be closer to the sun. A good example of differentiation is what happens if we have a rock sitting on an icy pond in the winter. Now the rock, of course, is more dense than the ice or the water, and in the spring, when the ice melts, what does the rock do? It plunges down to the bottom. Okay? The dense material in the rock is attracted more strongly to the earth than the water is, so we have this differentiation, dense material. Even in our own earth, dense material tends to accumulate at the center of the earth. Our iron core is much more dense than the rocky material around the edge. So differentiation can occur in a body like the Earth, where we have dense material at the core, and it can also occur in a system of bodies like the solar system. But the general idea is that denser material tends to accumulate closer to the center of gravity. All right, so as we work our way through our discussion of the other planets, we're going to be talking about the relationship between their semi-major axis and their orbital period. These numbers are all expressed in terms of Earth units, and we're going to look at Kepler's third law, the harmonic law, which relates to the square of the period to the cube of the semi-major axis. If we take this formula and we express it in Earth units, we can show that any pair of numbers here actually satisfies Kepler's third law. It's obviously true for the Earth, because for the Earth, the period is 1, the semi-major axis is 1 astronomical unit, and the orbital period is 1 Earth year, so we get 1 cubed equals 1 squared, and that's true. 1 cubed is 1, 1 squared is 1, so we get 1 equals 1. So that formula is kind of trivially satisfied for the Earth data. But if we look at Mercury, and we plug in 0.4 for A, and 0.24 for the period, we do the math, we find that 0.4 cubed is basically equal to 0.24 squared, which is about 0.04. So any pair of numbers here will satisfy Kepler's third law. The final column here gives the spin period in Earth days. Now notice again that if we look at Mars, the spin period is just a little longer than Earth's day. So it's a little longer between sunrises on Earth than it is between, a little longer between sunrises on Mars than it is between sunrises on Earth. Just a little. Mars' day is a little longer than our 24-hour period. But look at Mercury. On Mercury, the spin period is like 59 spin period of the Earth. Spin period. I already mentioned this, but we see two major classes of planets. I'll just go on a little bit longer on this particular topic. We see the classes be divided into two, the planets can be divided into two classes, the terrestrial and the Jovian planets. The terrestrial planets are the Earth-like planets that are relatively dense, as we just saw. Density is quite close to Earth density. Mars being a little bit lower, but still relatively close to Earth density. Terrestrial planets tend to be small, also, as we saw. The Jovian planets are characterized by Jupiter. They're much larger, have low densities, and actually are much farther away from the Sun. Let me just show a couple of little videos that my computer will cooperate here. Okay, so we'll force it. Yes, so let me just see if this work. Yes, we'll hopefully tweak it. Sorry, program. Let's see if this actually works now. Buy that on a first name basis. No. We just okay, so this is a dramatic visualization. Probably about 10 years old now. It's not really quite a dramatic visualization. But we see the spin of Earth. Now notice if we
this animation begins by placing Earth into perspective with the other three internal planets of our solar system. The four terrestrial planets have different colors, sizes, tilts, and spins. With some artistic license, we show here a rendering of these various aspects of comparative planetology. Note that for Venus, we are looking at a much faster retrograde rotation of its upper cloud deck, not the much slower spin of its hidden surface. For Mercury, its spin rate has been increased in order to display its prograde motion.
Okay, so let me just move this tab here. So again, if we look down from the North Celestial Pole, we would clearly see a counterclockwise rotation of the Earth. And when we look at Mercury and Venus, so if you look down at Venus, you're going to see a clockwise rotation, but very slow. But notice that Mars' rotation is very similar to the Earth. Counterclockwise is due from the North Celestial Pole, and with a similar period. Okay, let me see if I can show this Jovian here. So again, another dramatic visualization. Start off with Earth and we're comparing with Jovian.
The four giant gas planets are here compared with proper size and scale to each other and to planet Earth. These gas giants are known as the Jovian planets. We see their rich colors and their many varied rings, each revolving separately. Indeed, Saturn's inner ring has a period about twice as fast as its outer ring. The tilts of the planet's spin axes are rendered here relative to the plane of the ecliptic, including that of Uranus, which is nearly pointing at us.
Okay, so we just go through the last one. This is the most dramatic one. It has a little bit of a Star Wars influence, let's see. Because we're going to show us the interiors of the planet, but in a very dramatic flyover plane of the planet. We're very proud of it. Right. Oh, I didn't play it. Credits are so long when you didn't play.
This animation begins by showing the comparative sizes and colors of the Jovian planets. We can artistically take them apart, revealing their relative innards.
Get ready to duck down. Down.
All of these gas giant planets, especially Jupiter and Saturn, emit more radiation than they absorb, suggesting great heat within them. Jupiter and Saturn have very similar interiors of mostly hydrogen. Somewhat by contrast, Uranus and Neptune are also thought to have nearly identical structures and compositions.
Okay, so when we get a little further out, we will talk about exactly what really is going on here. But this is a structure totally different from Earth's structure. It's all gaseous all the way out until we reach this inner core, which is roughly the size of Earth. So you could sort of create Jupiter by taking Earth and putting an incredible amount of hydrogen gas around Earth to completely destroy Earth's atmosphere. And then Earth would just be sort of the core of a giant planet like Jupiter, just give you a little bit of perspective. All right, so we'll pick this back up again on Tuesday. Actually, we're off on Tuesday, right? So see you in a week. Have a great Columbus Day. Do whatever it is you do on Columbus Day. Yeah.